Hi again. In this lesson, you're going to learn about the clustering family of algorithms and how they can be applied to image segmentation. You're going to see the k-means algorithm, which can be applied to many domains. In the accompanying lab, we're going to write our own version of this algorithm before switching to OpenCV's version to complete training quickly.
Now, let's look at clustering algorithms. Many of you will be familiar with clustering for other applications. If you are, you might be interested to see how we can apply it to image segmentation. And if you've not encountered clustering before, now is a good time to learn how we can use clustering algorithms for image segmentation. Clustering is a powerful technique that's used in image segmentation. The cluster analysis is to partition an image dataset into a number of disjoint groups or clusters. Its key benefit is that it is unsupervised. That is, it does not need to be pre-trained. It is particularly interesting in certain fields, particularly medical imaging, where it gives reasonable results at reasonable computation cost. One can cluster around any number of properties in the image, of course, but today we will concentrate on clustering around RGB values. Relatively common used clustering techniques include k-means and related techniques, fuzzy c-means, FCM, and related techniques, and expectation maximization. Today we're going to illustrate the general principles of clustering algorithms by using k-means as an example to segment our starfish. There's a lab on this, so you'll get plenty of opportunities to work through this yourself. K-means can be used both for classification and regression problems. It is typically used for classification problems. It is a relatively popular method because of its simplicity and relative computational efficiency. K-means clustering aims to partition n observations into k clusters, in which each observation belongs to the cluster with the nearest mean. It assigns an observation into a cluster by using a distance function to ascertain the distance of the observation to each of the clusters. Normally the distance function is Euclidean distance, or as we normally think of it, just plain old distance. So we need to know the basic operation of the k-means algorithm. Choose k points to start from. Let these be our initial cluster centers. So then, until either A, enough loops have run, or B, not a lot is changing, then for each point, calculate the distance to each cluster center, note the shortest distance, and put the point in the cluster that's closest to it. Then, for each cluster, calculate the new cluster center. Don't worry about the starting and termination conditions too much for now. We'll turn to them once we've dealt with the main body of the algorithm. Let's start with the distance term. I think if we really understand this term, the rest of the algorithm falls into place pretty quickly. And we're all familiar with Pythagoras. Let's refresh our memory of how we can use Pythagoras' theorem for the length of the hypotenuse. We recall that we can convert 2 points, x1, y1, and x2, y2 into a right-angled triangle by introducing a new point, x2, y1, and thus we can solve the length between the two original points by deriving the square root of the hypotenuse. Now we can imagine a point at 4, 3 and 2 clusters. Let's say a green cluster with center 5, 6 and a red cluster with center 1, 1. So our goal here is to figure out which of these two cluster centers our point is closer to. So all we do is use our formula to determine which of the cluster centers is closer to our point. And if we solve for the red triangle, we see the x difference is 3 and the y difference is 2, and so if we square the two of them, that's 9 and 4. We add that together, we get 13. We get the calculator out and get the square root, and that's 3.6. Then for the green triangle, the x difference is 1 and the y difference is 3. So we square those, we get 9 and 1. We add them together, we get 10, and we get the square root of that, and we've got 3.2. So now we've decided our point is closer to the green cluster center than the red cluster center. Great. Now, we can illustrate the principles behind the algorithm using a small number of points, each with two features, x and y. But it's important to notice that we can use Euclidean distance for an arbitrary number of features. In our lab, we are using 7 features. So, for a two-dimensional image, we can say the distance is the square root of the square of the differences of the x's plus the square of the differences of the y's. Again, for 3 dimensions, we have the distance between 2 points is given by the square root of the difference between the x's squared plus the differences between the y squared plus the differences between the z squared. Now, let's rewrite the 3-dimensional form of the equation into a term derived from features. So what we're really doing here is saying that x is just a feature, y is a feature, z is a feature, and so on. Or we could use RGB values and say red is a feature, green is a feature, and blue is a feature. So we're getting away from our visual representation and rationalizing that we can use this distance function to calculate a distance between any number of features. So now we're saying our distance function is the square root of the difference between a feature 1 value and another feature 1 value squared, and the difference between a feature 2 value and another feature 2 value squared, and the difference between a feature 3 value and another feature 3 value squared. And again, in our example thus far, feature 1 is x minus xc, the distance in the x-plane between our point and a cluster center. And feature 2 is y minus yc, distance in the y-plane between our point and a cluster center. And feature 3 is z minus zc, distance in the z-plane between our point and a cluster center. But that mapping only exists in our heads. We can use the difference between any value and the same value at a cluster center. So we can change feature 1 to be the distance that our pixel's blue value is away from the blue value at our cluster center, and our feature 2 can be our pixel's green value, and feature 3 can be our pixel's red value. Or for that matter, any other arbitrary feature we think might be helpful to help segment our image. So, for 7 features, which we'll use in the associated lab, we can represent it as shown here, which is the square root of the squares of each of the 7 features we are interested in using to segment our image. In the lab, we'll discuss our feature choice a little more. Okay, now that we've grasped the basic trigonometry that we're going to use to calculate the distances between our points and our cluster centers, let's go back to our 2-dimensional example. Let's plot all the points in our very simple example. Remember, in the lab we are going to do something very similar to this, except with more points and more features. Okay, now we've got all our points plotted. Ultimately, in our example, we're going to divide our small set of points into 2 clusters. We start by selecting 2 points at random to start the process. I've rather deliberately chosen 2 unnatural points. We don't want to solve on the first attempt. Now, using our trigonometry, we go round to each point in our example and place it in its correct cluster. Again, you'll recall the algorithm is iterative. It's not supposed to solve on the first run. It's meant to iterate closer and closer to a reasonable solution. After that, we find the centroid of the points in each cluster. The simplest way to do this is to calculate the mean of every feature in our blue cluster and in our red cluster and store these values. Now you might notice I've turned all the original pixels back to black. Effectively, we now forget all the information we've built up and we're ready to start again. Finally, we start again using our distance function and looping across all our points, assigning each point to the nearest centroid to it. You'll notice that this time the cluster centers have moved sufficiently that the points seem to have a more natural distribution. We repeat this process until some termination conditions. Let's say, for now, we'll simply do it 100 times, and we'll see later a better way of terminating. This slide illustrates the k-means algorithm running. It's a visualization of our starfish image being segmented. Effectively, the 7 features we used are converted to XY values for each pixel in each cluster, and we can gain an insight into how the algorithm runs, and maybe an intuition as to how we might terminate it. Often in k-means, we watch an error term, epsilon, and terminate either A, when epsilon has become sufficiently small, or B, when we've run the algorithm sufficiently many times, for instance 100 or 1,000 times. So how might we calculate epsilon? If you recall, in k-means we have clusters, and each cluster has its own center. So the sum of the squares of the differences between the cluster centroid and each data point in the cluster can be thought of as an error value for that cluster. Epsilon can therefore represent the sum of the error values of all the clusters. We can fairly easily construct a loop to stop when this value of epsilon is below a suitable threshold. Often, if you plot the result of epsilon over time, you can see an elbow or a knee in the data, and continuing to process beyond this elbow or knee is usually unproductive. You can probably imagine a couple of different ways of initializing the clusters. Two commonly used initialization methods are Forgy and random partition. Forgy randomly chooses k observations from the dataset and uses these as the initial means. Random partition first randomly assigns a cluster to each observation and then proceeds to the update step, thus computing the initial mean to the centroid of the cluster's randomly assigned points. K-means is reasonably computationally expensive. Normalization of the variables must be performed wisely, otherwise higher ranging variables can bias the algorithm. This can lead to a degree of hand tweaking as you adjust the relative weights that your features contribute until you're satisfied your k-means is running effectively. Also, it can be difficult to predict the value of k, i.e. the algorithm will partition into two segments if it's programmed to do that, but it is not able to decide itself how many clusters is appropriate. Different initial partitions can result in different final clusters. It's reasonably well known that the output of k-means depends on the initial seeds and the predefined number of clusters. Finally, it is not effective with clusters of different size and density. One way of looking at fuzzy c-means and our expectation maximization algorithms is that they are attempts at clustering which ameliorate these drawbacks in k-means. They often allow the feature vector to have multiple memberships to multiple clusters, and they can offer better results, but at a computational cost. So to wrap up, k-means is a well-known simple algorithm. It is capable of adaptation to image segmentation, and it's reasonably popular in medical imagery. It has some well-known limitations, and if you're interested in clustering, there are improvements such as fuzzy c-means.
Okay, now you should have gained an insight into how you can use a clustering algorithm to segment an image. We've introduced how important selecting and weighting features is. As we move forward in the course, keep in mind how much experimenting you did here around feature selection and weighting. As you'll see, the amount of handcrafting changes as our techniques evolve.